All right, chemistry class, good day. Before we go into today's lesson, things are going to start getting harder. Okay, so this is the lesson about light and quantized energy. We're going to break it into 2 weeks because it's very confusing. In order to understand the way electrons behave and the way, like chemical behavior in general, we got to talk about the dual nature of light because that's partly how they figured out things. But before we do that, okay, our last 2 lessons were defining the atom and how atoms differ, okay? And I want you guys to make sure you understand those 2 lessons good and you've done the review questions. I want you to take photos of the review questions and send them to me in my email, okay? Because I want to make sure you understand this stuff good before we do this new lesson. And today's lesson, there will be problems you can practice on your own, but I'm not going to assign any new problems to give you time to make sure you've done the old problems and you understand what's happening before we get into this new stuff, okay? So once you've done the questions from defining the atom and how atoms differ, okay? And I remember I did videos answering the questions, so you should be able to answer them. If you have questions, let me know, okay? But then once you finish those questions and you take a photo and send them to me, then watch this video, this new lesson, all right? All right, here we go. So today we're going to talk about the dual nature of light and quantized energy, okay? So when we left off, remember Rutherford's model, we talked about what the atom's like. It's positive in the center, electrons moving around the outside, right? So that doesn't explain things. There's things that are unexplained. So for example, right, if the center is positive and the outside is negative, why don't the electrons just get attracted to the center? Like a magnet. Magnets, opposites attract. Negative wants positive. So then how come in an atom the electrons don't just go to the nucleus? How come? How come like differences in chemical behavior, which is like when you're in the same, hopefully you guys learned this. There's the columns and there's the rows, families, and periods on the periodic table, right? How do you explain those traits? Like chemical behavior is what it's called. How do you explain chemical behavior on the periodic table with like elements that are in like different periods, same family? How do you explain that? Okay, they couldn't explain that with Rutherford's model. And you couldn't explain, like, where are the electrons or how are they arranged? Like Rutherford said, oh, there's a nucleus and there's electrons, but he didn't explain how the electrons are arranged. So all these questions, okay, were leading scientists to try to figure this stuff out. And they did the flame test. It's called the flame test, okay? And they revealed, the flame test is where you just put the element in fire, okay? And when they did that, what they saw was that the chemical behavior of elements is related to the arrangement of electrons in atoms, okay? And what that means is, that's significant because that means since each element has a different number of electrons, that is how, that is why they behave differently chemically. That's why hydrogen's a gas, and neon is a different type of gas, but why they're not the same, that all has to do with the electrons, like we talked about in the last lesson, okay? So they did the flame test, and that related to okay, sorry, I'm getting ahead of myself, but that's related to the chemical behavior of electrons arranged in atoms, okay? And this stuff's all in your energy system lecture, okay? So that leads us into the 2 natures of light. Light has 2 natures, which is very confusing. It doesn't really make sense to me still. Like, it's just confusing how it can be both all the time. It's like Jesus, fully man, fully God. How does that work? Well, it's confusing, okay? So the wave nature of light. Electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. Okay? So, basically, light is a form of electromagnetic radiation. Okay? And we'll talk about that in a sec. There's lots of forms of light that we can't see, that aren't visible. I'll show you my drawn diagram in a little bit. It's pretty rough, okay? And it's an energy system as well. So you'll look at that, okay? And you remember talking about waves, I think. We'll get into that in a sec. But visible light, the light we can see, is one form of electromagnetic radiation. Okay, so light can behave as waves. That's the first one we're going to talk about today. It's a wave nature of light. Okay, so wavelength. You guys remember wavelength. I'm going to show you. Wavelength is a distance, the shortest distance between equivalent points on a wave. So if you're at the top of one wave, it's the distance to the top of the next. That's the wavelength, okay? Distance between shortest points on the waves. You can measure that in nanometers, centimeters, meters, okay? Different ways to measure it. Just keep your units consistent, okay? All right. Frequency, remember frequency is inversely related to wavelength. So frequency is how many waves are at a certain point. So you could have one wave at this point, or lots, boom, 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 boom. That's more mass frequency. Mass frequency, more frequency, okay? That is, so frequency is 1 over seconds, or inverse seconds. So it's how many waves pass a point in 1 second, is what that is, okay? Number of waves that pass a given point per second. And then amplitude is the height of the wave. So either if you have more waves or less, amplitude is from the center. That's amplitude. So up or down, that's amplitude. And amplitude does not depend on if it's more frequent or less frequent or wavelength. Okay, it's independent of those two. Okay, so let's look over here at my nice drawings. Definitely not an art major. Okay, you can see that. So you can see right here is amplitude, distance. Here's amplitude. These aren't very good drawings. Look at the ones in your book, okay, or in edit system. But amplitude is this: the distance from the middle, the nodes, to the peaks, okay. And then wavelength, right, is the distance from crest to crest or trough to trough, okay. So you can see which one is more frequent in this time span, right? This one, violet, this is a violet ray, okay? It's more frequent because look, in the same amount of time, there's 1, 2, 3, 4, right? And this time there's like 1.5, 1.5, okay? So it's more frequent, but the wavelength is shorter. So when there's more waves, the wavelength is always shorter, and when there's less waves, the wavelength is always longer. They're inversely related, okay? And that brings us up to the wave. We have the wave equation, electromagnetic wave relationship, okay? C equals wavelength times frequency, okay? So C is the speed of light, which I remember we talked about this. Hopefully this is a review, okay? Talked about this. The speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. That's in a vacuum, so that's like in space. So it's different when it travels through air, or it's, it's close to the same. But it's different through water, it's different through ice, it's different through different things. But that's the speed of light we use when we're calculating things, okay? Wavelength is what we just talked about. That's the symbol for wavelength. Remember, crest to crest or trough to trough, okay? So it's traveling like this, wavelength, okay? Frequency is this kind of funny V shape, right? And frequency is how often the waves, right? How many waves, number of waves that pass a given point per second, okay? That's frequency. So these are our 3 variables in the equation, okay? Those are our 3 variables, all right? So with that, we can do some problems, but we won't quite yet. Remember, we did this in class, so hopefully these problems will be a review. But basically, that's the relationship. So in order to solve for one of these other variables, you just rearrange the equation. Because you'll always know the speed of light, okay? Because you always know the speed of light is 3.00 times 10 to the 8th. Remember, scientific notation, we talked about that a little bit before you guys left. But okay, so over here, please look in Eddy System for this as well. But over here is the electromagnetic spectrum that I tried to draw just to give you guys a feel for it. Okay, and the big takeaway from this is you see this little tiny section over here? See this little tiny section over here? Right? This section is the visible section that we can see. So this whole thing is the electromagnetic spectrum, and they're all waves. But the waves of light that we can see are just this tiny little section. In between 10 to the 14th and 10 to the 16th frequency, hertz and hertz. Okay? In between those, like just that little section is the visible light. See, so I blew it up here, and then it goes in order. Roy G. Biv, the colors you can see, okay? So, that's visible light. Red is red, orange, yellow, green, blue, violet, right? So that's the progression of the wavelengths, okay? Violet, shorter, more frequent, right? Red is longer, okay? So, then you can see, here we are, these are longer rates, so like, here, I'm going to try to do this. So these are longer, oh, this marker is giving me nothing. Come on, marker. Oh, no. Wake up. Okay, sorry. So here they're longer, like this, and they get shorter, and 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 then they kill you, okay? That was not the best drawing. But here's the deal. So we start off with radio waves. So it's like when you're listening to waves on the radio, exactly the same. Okay, and those are real long. Okay, real long waves. And then you get into the microwaves, which are a little bit, like sorry, when I say real long, I mean they're not very frequent. They have really long wavelengths. Okay, so they don't happen very often. They're real slow, not dangerous. Okay, microwaves getting a little more dangerous, right? That's how you cook food. So they're more frequent, and they have less smaller wavelength. They're getting smaller. You can see they're getting smaller. Okay, and then we get into infrared light. Okay, it's getting a little bit more frequent. And then there's a little section in there that's visible light, right? The little visible light section. Not very big, but it's there, okay? Little visible light section. And then after the visible light section comes ultraviolet. It's tiny. That's pretty small. And that's dangerous. That's how you get sunburn. That's ultraviolet rays from the sun, okay? Ultraviolet comes next, and then X-rays. X-rays, that's why if you've ever broken a bone, you have to wear the lead vest to keep you from getting X-ray radiation, because it's dangerous. So X-rays are becoming more frequent. Shorter wavelength, it's getting shorter, okay, that's X-rays. And then the last one, the shortest, the most frequent, is gamma radiation, and that kills you. If you get a gamma radiation, you will die. So that's just like, like really, really up and down, the waves are just like this. So the more frequent the waves are, the more dangerous they are. And the less frequent they are, and the bigger the wavelength is, the less dangerous they are, okay? So you can read about this more in any system, but that's pretty much my crash course on the wave. So this is not a good drawing. But the big thing too is as the energy increases, right? Gamma rays have more energy, radio waves have less energy. The wavelength decreases. So this way, right? Gamma rays have like tiny wavelengths because there's just so many of them, right? And then the opposite way, as the wavelength increases, the frequency decreases. Right? So as radio waves are really big and long, there's less of them. Okay? That's important to see. So this is not a very good drawing, and you're probably really confused. So look at any system, and that will make things better. Okay? So the last thing I want to do in today's video, because I'm sure you guys are going to be really busy doing the homework from before, right? The last thing I want to do is do this problem that we already did. Remember, we did this problem in class, but I just want to refresh so you guys remember, because this is important. Being able to solve problems using equations is important. And that's because this is like, this is some pretty important stuff, okay? So, here's our equation, right? Number C equals wavelength times frequency. So problem 1, this is from any system. Microwaves are used to cook food and transmit information. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9 hertz? Remember, hertz is 1 over seconds, okay? So, well, how do we do this? Well, we have our equation, and we know c, speed of light, is 3.00 times 10 to the 8 meters per second, right? And we know the frequency is what they give us, 3.44 times 10 to the 9 hertz, okay? So what we want is we have c equals wavelength times frequency. We want this by itself. So you divide by the frequency. So you divide the speed of light by the frequency. So then you have c over the frequency equals the wavelength. And then you plug in your numbers. So we have 3.00 times 10 to the 8 over 3.44 times 10 to the 9 equals 0.0872 meters. But we want that in scientific notation, remember, because that's how we do this. So that in scientific notation, that's 8.72, times 10 to the minus 2 meters. Sorry, that's perfect. Okay. So both are the same answer, but they're different ways of getting there. Okay. So what I want you guys to do some practice problems on your own. I'm not going to assign any new homework, but do the assignments from the last two assignments, and take photos of them and send them to me. And then next week, we'll talk about the particle nature of light. Okay. See you guys next week.